Before moving forward in this course, we need to learn how to create Bitcoin address. And for that, we need a elliptic curve library. You can find this library attached in your course material. Go ahead and download it. Once you have downloaded the library, go ahead and copy it inside the code directory. I have copied the library inside the code directory, and we need to also create another directory inside the blockchain directory. That would be client. And inside the client directory, we need to create new module called account. Alright, so now we need to create a class called account. So in this class, we will create our Bitcoin address. So create class account. We really don't have anything to initialize in this class, so we are not going to define the init method. So let's define the function called create keys. So before we start creating our Bitcoin address, we need to learn a little bit about the elliptic curve. So let's understand what is elliptic curve. So the equation for the elliptic curve is y square equals to x cube plus ax plus b. And we are using a very specific equation in elliptic curve, that is SECP 256K1. So the same equation is being used in Ethereum and many other cryptocurrencies. And what is special about this curve is the parameters or the constant values. So in this curve, the value of b is 7 and the value of a is 0. And the final equation will be y square equals to x cube plus 7. We are also going to use few constant values. These values are predefined in elliptic curve and they are constant. They won't change. So the values that we are going to use is gx and gy. So these are the values. So this is nothing but your numeric number, but right now it is in hexadecimal representation. So let me quickly show you the number in numeric form. And to create the Bitcoin address, we need the gx and gy coordinate, and these two coordinates are predefined in SECP 256K1 curve. And the gx and gy coordinate is somewhere on this curve, and since those values are constant and they are predefined, and we are going to use those values now to create our public address. So let's go ahead in our VS Code. And these are the values for the gx coordinate and the gy coordinate. Right now these values are in hexadecimal format, but these are really the numeric numbers. So let me show you quickly the gx coordinate in the numeric form. Type Python, paste your gx coordinate, and you can see the value is in numeric format. Same is for the gy. Copy gy coordinate, and this is the numeric value for the gy coordinate. All right, let me close the terminal and let's start by importing few classes from the elliptic curve library that we just imported. So first we need to import our class called SHA-256 point. So let's go ahead and import it from blockchain dot backend dot core elliptic curve import SHA-256 point. We need to also set the path, so where it should look for these libraries. So go ahead and import sys.path dot append, and you can find the path from your terminal. So for me, this is the path. You need to change the slashes to /. Okay, so we have set the path, we have imported the library. Now we need to create the instance of our class. So go ahead and create the instance G SHA-256 point, pass gx and gy to our class, and now we have the instance G for this class. So the elliptic curve equation that we just saw here, that is defined in SHA-256 point, and we need to also import one more library that is called secrets. So let's go ahead and import secrets. So this library is required to create the private key, and we have chosen this library for a very specific reason, because your private key is at the core. We need to create our private key in such a way that it is not easily identifiable or nobody can easily crack it. So that's the reason we are using this cryptographically secure library secrets. And let's go ahead and create our private key. Private key equals to secrets dot random bits, and we are going to give the random bit size as 256 bits because that is the size of our private key, 256 bits. And let's go ahead and print our private key here. Okay, name equals to main, create the instance of our account class, ACCT equals to account. Nothing to pass here because we do not have any init class, so we are not passing anything here. And go ahead and call the create key function, ACCT dot create keys, save it and run. Alright, so we have the private key here. Now every time you run the script, it will always give you a unique private key. Alright, so we have a different private key here. Okay, so until this step, we have everything working. So let's clear the terminal and close it. Let's remove the print statement. In our next step, we are going to create our public key from here. So let's go ahead and create the public key. Creating a public key is very simple. So it's a simple multiplication. We are simply multiplying the private key with our G point that we created here, and it will give us the uncompressed public key. And we will also see how to create the compressed public key from that. So let's go ahead and create the uncompressed public key first. Uncompressed public key, private key into G. So this will give us the uncompressed public key. So basically this is returning the x coordinate and y coordinate on the elliptic curve. And now we will extract the x coordinate and y coordinate from the uncompressed public key. So let's go ahead and do that. X point, uncompressed public key dot x, copy it, and we will do the same for the y coordinate. Just change the value from x to y, and same for the y point. Okay, so now we have the x point and the y point. Now if you will look at it, we really don't need the x and y point together, because we can easily calculate the x point from y and y point from x, because our equation is y square equals to x cube plus 7. So if we have y, we can easily calculate x from it. So this is how we are going to compress our public key. So we are going to use just one of the point, and we will use the y point in this case. So let's go ahead and see if y point is an odd number or the even number. So this will tell us the y point is the even number. If it is a even number, so we will add a prefix of 02 in front of it. So let's go ahead and define it. Compressed key bytes. So we are going to define that in bytes format. So x02 plus the x point that we created here. So we are going to convert that x point to bytes because right now it is in numeric form. So let's define x point, and there is a simple function to convert it to bytes. And also we need to define the size of the key. So this is 32 bytes long, so we'll define 32 bytes. And also we need to define if it is a big endian or the little endian. If you don't know what is big endian or little endian, it's a very simple concept. So in big endian we write the number from left to right, and in little endian we write the number from right to left, and that is in bytes representation. So let's go ahead and define big endian here. And if it is not an even number, so we will prefix it with 03. Copy this line and paste it in the else. Change this to 3. In the next step, we are going to run a couple of hash functions to create hash 160. So first we will do the SHA-256 hash, and whatever the output is coming from that output will be passed to RIPEMD160. That's another hashing algorithm. And then we will have the hash 160, the final hash. Let's go ahead and define that in the util module. So go back to your blockchain backend. Open util. So we need to import a library called import crypto.hash. From crypto.hash import RIPEMD160. We will define the function hash 160. So this will take the input. Before we do that, we need to import one more library called hashlib. So from hashlib, we are going to import SHA-256. From hashlib, import SHA-256. Return. So first we will do SHA-256 on whatever the input is coming. Then do digest. And whatever the output is coming from that, we will run the RIPEMD on this. So let's go ahead and do RIPEMD 160 dot new. Change this to lowercase s, and whatever the output is coming from this, do the digest for this. And this add back to account, and we need to import hash 160 from the util package. So let's go ahead and do that. From blockchain dot backend dot util import hash 160. So let's put this up. All right. So now that we have hash 160, so let's go ahead and run this function. We will store the output in hash 160 to hash 160 and pass our compressed public key that we just created in this step right here, and this will give us the RIPEMD final hash. So define prefix for mainnet. The Bitcoin mainnet prefix is 1, so we are going to use the same prefix, main prefix. So this is in bytes form. Okay, so we have defined the main prefix. Let's go ahead and add the main prefix to hash 160 that we just created in the step above, and define this as new address, main prefix plus hash 160. In the next step, we are going to define the checksum. So checksum is really important while creating the addresses. So it will capture if there is any error in your address while you are transferring money to somebody. So it will capture it. So what it does is, so we are gonna do the hash of this address, and we are going to pick up the first 4 characters from the address and add it in the new address. So let's go ahead and do that. Little documentation about checksum. Checksum equals to, so this is the hash 256, so which means the double hash. So we have already defined the hash 256 here. So we are going to do 2 rounds of hash of this address. So let's define new address, pick up the first 4 characters of the address, whatever the hash is coming from it, assign it to checksum, and the new address is new address plus checksum added to it. All right, so we have added the checksum. In the next step, we are going to define the base 58. Base 58 is nothing, it's just the values or the numbers from 1 to 9 and your A to Z ABCD, and then A to Z your lowercase ABCD. Define count. So in the next step, check for how many zeros are there in our address, and we are just checking the leading zeros in address because we are just concerned about the leading zeros. So let's go ahead and check that. New address, if C equals to 0, then increment the counter that we defined, count variable, else break, because we are just concerned about the leading zeros. In the next step, we are going to convert our address into numeric form. Let's go ahead and do that. Number equals to int from bytes, new address, and it is in big endian, so we need to tell if it is big endian or little endian, and it will convert accordingly in the numeric format. And in the next step, we will do prefix 1 into count. So basically, how many zeros we have found in the address, so we are gonna convert that many zeros in the prefix. We are just multiplying that many ones with that number. And let's define result equals to blank. And so in the next step, we need to find a way how to assign the base 58 values to this number. So we need to create a while loop here. Inside the while loop, we are going to use the method div mode and pass number here and divide it by 58. So this will give us 2 values in return. first the number and second the mod value, and your mod value will always be under 58. And in the next step we are going to do result base 58 alphabet, whatever it is returning here in the mod, so assign it here mod plus result. So let's quickly see what it is doing. So we are dividing it by this number, it will return the mod value, and we know that mod value will always be under 58. So whatever the value is coming here, for example we got 57 by dividing whatever the number is there, so it will pick up the number from the location 57 and assign it to the result. It will keep doing until we have assigned all the values from our number to the result variable. And I think we are done with this. So in the next step, let's go ahead and assign the prefix that we created in the step above to the result. So the public address is prefix plus result. There is a difference between the public address and the public key. So public address is the final output after doing the base 58 conversion, but your public key is this one, the compressed public key that we created in this step. So there are a couple of steps involved after creating the public key. So we did the hash 160, and then in the next step we have assigned the main prefix, the main net prefix, and we have also created the checksum, and in this step we have assigned the base 58 values to our public key, and now we have the final public address. Let's go ahead and print the private key and the public address that we created. So print private key, and the public address. Let's remove all the spaces from here. Okay, so let's go ahead and quickly check our code if everything is okay. So we have created the class create keys, we have created the private key, we have got our uncompressed public key from here. So we are checking if the y point is odd or even number, and we are assigning the tag accordingly. In the next step we are doing the hash 160 here, and okay, so change this to lowercase x, and also here change it to lowercase x, and also we missed to get the number because change it to number. Save it, and let's go back to the utility function, and we have the hash 160. It is simply returning the hash, whatever the input we are passing here, and this looks good. Let's go ahead and run it now, and you can see we have the private key, and we need to change the text here to public key. Let's save, delete, and rerun it again. Okay, so for this private key we got this public key, so this is working as expected. Let's run it one more time. Nice. So for a different private key we are getting the different public address, and we can see it is starting with 1 because we have defined that this is our main net address.